Oh, yeah.
I say like you play on the left.
And hopefully it's not.
I got the two body.
It was supposed to be like, so it's like, yeah.
Bring this in. Bring this in.
Like,
I do it all the time.
every day. I think they sold it.
Yeah.
Yeah. I remember the white pill, the goggles as well.
You know, I did all that.
I just like it's fine.
I couldn't look at this. I didn't put off.
That's really bad. I think I don't know. But
It's a left line.
it's not worth
Oh, yeah. No, not the same.
Yeah, see.
Like. But if you also need that.
Expert problem.
Sure.
I think it's just.
You know what, I see, I look. Do my tools are like.
Yeah. Right.
Yeah, I really think I should just.
Yeah, but how do you finish?
Usually I would say
It's usually not.
I know. We got all the I got it on the pocket. Much of the same, like, they're from the three pencils. Like, first, it's a friend, right?
It's such a different.
Yeah.
So.
Well, can you hear me? Can you hear me, Jordan?
That's one of the things we are bringing up, trying to get on my.
Threshold might be one.
It's going. Hmm.
See that here.
Can you how about this? Better? I don't really see the other one. Okay, well, I mean hopefully the volume comes back, but it's 4 o'clock. Let's go ahead and get started. How's everyone doing today?
Good.
Good. I'm doing good. Thanks for asking. It's week 2. Oh, okay. It's just okay. I don't know what else to say. We gotta start class. You better run fast. All right. So plan for today is we're going to be continuing our discussion of differential equations. So we had one example to finish up from last time on first order equations. We're doing integrating factor, and then we're moving on to second order equations. So moving pretty quickly. Other announcement I wanted to make was that homework 1 was posted. So some of you may have noticed this on Friday. So I think I may have put in a typo. I think probably either on Canvas or on the document. But the due date is actually this Friday, January 30th. And so after today, you'll have everything you need to do that homework assignment. Because that homework is just first order equations. So you should have everything you need to do it by this Friday. Okay. Our next homework, which will be on second order equations, I will post next week. But we'll be spending quite a bit more time on second order equations, so you have a bit more time to do that one. But for first order stuff, there's not really that much to cover with first order equations, so that's why it kind of has an early due date. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. So last time we were here, we were discussing first order equations with integrating factor. Okay. All right, so the idea with first order with the integrating factor is the following. So if we have an equation that looks like this, so we have dy dx plus p of x times y is equal to r of x, right? So this is our stereotypical kind of linear first order equation, right? It's linear in the sense that everywhere that y occurs, it only occurs in the first polynomial order, right? Right. So all y terms. All right, so the coefficients in front of the y terms, those can be functions of x, but we don't place any restrictions on that. So the only restriction we have is that all the y terms have to have exponent 1. Okay. Now, what we said for these equations is that, unlike our separable equations, we can't really just use straight up algebraic operations to get this into a form where we can solve, right? But, since this is just a first order equation, in theory, if you have just a first order derivative, you should be able to just perform one integral in order to solve it, right? And so the whole idea with integrating factors that, is there some way we can manipulate this equation in order to get it to a form where we can just directly integrate to find the solution? Okay. All right, and so there is a way to do that, and so it's a little bit of a contrived kind of weird solution, but the way that we can obtain that is by multiplying this entire equation by another function, which we call the integrating factor. Right, and so if we define a new function, so traditionally we give this function the symbol mu, right? And so we say that mu is equal to e to the integral p of x dx, right? Where this p of x, you get that as the coefficient in front of the y term. Okay. And so if you multiply the entire equation by this factor, you kind of do a little bit of kind of algebra, a little bit of, reverse product rule. We did that derivation last time, so I'm not going to repeat it here today, right? We end up with the following. So we get, after some work, we get d dx of y of x mu of x is equal to mu of x r of x. Okay. Right, and then from here, what we can do is we can take the left-hand side of the equation and just directly integrate that in order to obtain y of x. Okay. So you'll see me use the acronym LHS, RHS a lot in this class. So LHS stands for left-hand side, RHS stands for right-hand side. Okay. Okay. So that's the idea with integrating factor. So the most important thing is we have to kind of define and compute what this integrating factor is, and then use that to solve our equation. So we're right in the middle of a example. Okay. So the example we were doing was the following. So we had a simple RL circuit with a DC battery. All right. So our circuit looks like the following. So we have a resistance here. We have an inductor, kind of a wonky inductor. And we have our battery here, okay? Okay, so when you connect this circuit, we have kind of a closed loop here. Electric current is going to flow, right? All right, so we use the symbol I to refer to the electric current, okay? And so the differential equation that that is associated with the current is the following. So we have di dt plus R over L times I is equal to E over L, okay? Where in this situation, all of the parameters in this equation, except for the current I, are constants. So R, resistance, inductance L, and the battery voltage E are all constants. Okay. All right. And so given the situation, we want to solve for an expression for the current as a function of time. All right, so that's what we want to do, okay? All right, any questions on, sorry, I should have paused after the recap. Any questions on just anything so far? Good. Okay, all right, so let's go and solve this. So what we have here is a linear equation, right? So it fits our criteria. So our dependent variable I only appears in linear form. So all the terms with I, its derivatives are all exponent 1, okay? So this fits the bill for a linear equation. It's also non-separable because we have that extra term on the right-hand side, the E over L. So it's not possible for us to just use algebraic methods to separate this equation. So the only way for us to solve this is to use integrating factor. All right, so first let's compute what our integrating factor should be. So we have mu of t, right? I know up above I defined integrating factor mu of x, but x and t are just the independent variable. So it just depends on whatever your equation is. In this case, we have time as our independent variable. Okay. Okay, so our equation for this should be e raised to the integral of p of t dt, right? So let's just go ahead and plug in our expression for p of t. So p of t here is just the coefficient in front of I in our governing equation, which is just r over L here, okay? All right, so we plug that in, we get e to the integral r over L dt. Okay. So since r and L are just constants, and so that's just going to integrate, that's just performing integral of 1. And so our integrating factor in this case is e to the r over L times t. Okay. All right. So now that we have our integrating factor, we are set to go ahead and plug it in. And so, so let's do the full thing right now. And then for the next example, we'll go a bit more quickly, but just to kind of remind you why we do the integrating factor. So let's multiply entire ODE by mu of t. Okay. And so if we do that, we get e to the r over L times t times di dt plus e to the r over L t times r over L times I is equal to e over L times e to the r over L times t. Okay. So all I've done is I've taken our original differential equation that we started with for this problem and just multiplied the entire thing by our integrating factor. Okay. Okay. All right, so here's the whole key to the whole integrating factor approach, right? So if we look at the terms here that I've boxed here, or the ones that I've kind of highlighted, right? Those, if you look at that, right? We have the product of e to the r over L times t times r over L, right? If you look at this carefully, right, and this was intentional, so this was kind of the reason why we picked this form for the integrating factor, right? This is nothing more than just d mu dt, right? Okay. Because if you look at our expression for mu of t, so if you look at this expression here, right? If you take the derivative of this with respect to t, right? So basically take d dt, and what we get is r over L times e to the r over L times t, okay? Right? That's why we picked this form for mu of t, so that we can get this derivative of the integrating factor directly into our expression, okay? And so what we have here is if we have that collection of terms as d mu dt, this term right here is mu of t, okay? So we have mu of t times di dt plus d mu dt times I, right? That right there is our product rule. And so if we do kind of our reverse product rule on the entire left-hand side, right? What we get is d dt of e to the r over L times t times I of t is equal to, the right-hand side stays the same. So it's e over L, e to the r over L times t. Okay. All right. And now this is good because now that we have a perfect, we call it a perfect differential on the left-hand side, we can now just simply take the integral of that left-hand side to cancel out that perfect differential. Okay. Okay, so if we integrate both sides, right? So we basically take the integral of this with respect to dt. We take integral of this with respect to dt. Okay. Left-hand side, the integral and the derivative are just going to cancel out. So that's going to cancel with this. Okay. And so on the left-hand side, all we're left with is e to the r over L times t times I of t. Okay. And on the right-hand side, we have integral of e over L times e to the r over L times t. Okay. And so we perform that integral, we get e over L. Integral of that is going to be L over r, e to the r over L times t. Okay. And then we need to add our arbitrary constant here. So that's plus c. Okay. All right. So we're basically there. And so the last thing we need to do is just simplify this guy. And so let's go ahead and simplify. So the L's here are going to cancel out, right? And then in order to isolate I of t, we're just going to divide both sides by this. Okay. Another way you can cancel that out is you can multiply it by e to the negative of that exponent. Okay, it's the same thing. And so then all we're left with after that is I of t is equal to e over r plus c e to the minus r over L times t. And of course, this here is a general solution because it's only specific up to that arbitrary constant c. We weren't given an initial condition in this case, so we can't solve beyond this. And so this is as far as we can take. All right. Any questions on how we did that example there? Good. Okay, all right, let's do one more example with integrating factor before we move on to second order equations. This one I'm going to go a little bit faster, but I think if you see it full speed, I think it kind of helps things as well too. Okay, so in this one's not a physical example, unfortunately. This is just a math problem, but we have x dy dx plus 4 times y is equal to 8x to the 4th power. Okay. And in this case, we do have an initial condition. And so our initial condition is y of 1 is equal to 2. All right, and so just like the last problem, we want to solve for an expression for the dependent variable, which in this case is y of x. All right. All right, so once again, if you look at this equation here, it is a linear equation. So all of the dependent variables y, they only appear with a polynomial order of 1. So, it fits our criteria for being linear. It's not separable. And so if you try to separate the equations here or separate the variables, you are not able to do that. And so the only way we can solve this is through integrating factor. Okay. All right, so first thing we have to do before we define our integrating factor, we didn't have to do this on the last problem because the equation I gave you was already in standard form. But first thing we have to do here is to get this equation into standard form. Okay. And so if you recall from last time, we defined what standard form was. So standard form, all that means is that the coefficient in front of the highest order derivative has to be 1. Okay. And so we don't have that right now because if our highest order derivative here is dy dx, and so the coefficient in front of that is x. And so first thing we're going to do is we're going to divide this entire equation by x just to get this into standard form. Okay. And so if we do that, we get first term is dy dx, which is perfect. Okay. Next term, we have 4 divided by x times y. And then on the right-hand side that we divide by x, that's going to take 1 power off the x there. And so we get 8x cubed. Okay. All right, so now that we have our equation in standard form, we are ready to do our integrating factor here. Okay. So let's compute integrating factor. All right, so our integrating factor mu of x is going to be e to the integral p of x dx. Okay. Let's go ahead and plug in for p of x. So p of x in this case is 4 over x. Okay. So that's e to the integral 4 over x dx. Okay. Essentially what we're doing is we're doing the integral of 1 over x, right? Because that 4 is just a constant that just comes out, right? And so integral of 1 over x is ln of x. And so you have e to the 4 natural logarithm of x. Okay. Right. Now we have to do a little bit of I would say obscure math here. So you have to kind of remember some of the properties of natural logarithms. And so one of the properties of natural logarithms is that if you have a constant coefficient out in front like this, right, you can actually bring that inside the natural logarithm, but it becomes an exponent of whatever is inside the logarithm. Okay. And so basically what we're gonna use the identity that 4 times ln of x. Another way we can express this is ln of x to the 4th power. Okay. So that 4 essentially comes inside the natural logarithm and it becomes the power of x. Okay. And this is from the properties of logarithms. Okay. And so if we do that, we get e to the natural logarithm of x to the 4th power. Okay. Next thing we'll notice here is that the e and the natural logarithm are reciprocal operators, and so those two are going to cancel out. Okay. Right. And then all we're left with then is just the argument inside the logarithm, which is x to the 4th. Okay. So our mu of x here, our integrating factor, is going to be x to the 4th power. Okay. All right. Any questions on how we got that, the integrating factor there? Okay, good. All right, so let's go ahead and let's go ahead and multiply this through. Okay. Right. And so I'm going to combine kind of 2 steps in one, just because we already kind of saw this in the last example. But I'm going to go ahead and multiply this ODE by this integrating factor, and then do our reverse product rule in the same step. Okay. All right, so if we do that, what we get is d dx of x to the 4th multiplied by y of x is equal to 8x cubed multiplied by our integrating factor, which is x to the 4th. And so we multiply those two, those exponents will kind of add to each other. So we get 8x to the 7th. Okay. All right, so now it's in kind of the perfect form. So let's just go ahead and finish up this problem. So let's take this. Now that we have our perfect differential on the left-hand side, we can go ahead and perform our integral. And so if we do that, we get. So we're going to take the integral with respect to x. And so on the left-hand side, the integral and the perfect differential are going to cancel out. And so left-hand side, we're left with x to the 4th, y of x. Okay. Right-hand side, we have integral of 8x to the 7th power. And so that's a pretty simple polynomial integral. And so we're going to do our reverse power rule. And so that's going to give us x to the 8th power. Okay. And then we have to add our arbitrary constant, which is c. Okay. All right, and then last step here is we're going to just simply simplify. And to simplify, we're just going to divide both sides by x to the 4th. And so we do that, we get y of x is equal to x to the 8th power divided by x to the 4th is x to the 4th plus c divided by x to the 4th. And that gives us our general solution. All right, any questions on how we got the general solution for this this problem here? Okay, good. All right, so, but we do have one more step on this problem because we were given an initial condition. Okay, so let's go ahead and apply that. Okay. So our initial condition in this case is y of 1 is equal to 2. Okay. So let's go ahead and plug x is equal to 1 into our general solution and set it equal to 2. Okay. All right, and so if we do that, we get 1 to the 4th power plus c over 1 to the 4th power, and that equals 2. Okay. All right, so if we go ahead and simplify this, we're not 1 to the 4th power is just 1, and so we have 1 plus c is equal to 2. All right, we simplify this, we simply get c is equal to 1. Okay. All right, so we go ahead and plug that back in, and then we finally have our particular solution for this problem, right? And so we have y of x is equal to x to the 4th plus 1 divided by x to the 4th. So that's the final solution to this problem. Solution to the original differential equation plus the initial condition. Okay. All right. Any questions on this? Okay. All right. So that's first order equations. And so, very, I know we went very fast with it, but I was just telling someone before the class that first order equations, you have to start there. You can't really just start with second order equations, but first order equations, there's not too many applications for it. And so, there's not too many interesting practical first order equations. And so, what we're going to do next, I think, has a lot more interesting applications, and you'll see kind of a wide range of them, which are second order equations. Okay. All right. So let's talk about some of the applications first, or let's just preview them. So you kind of know what's coming. Okay. Okay. So when we first introduced first order equations, we went over an example in heat transfer, right? Second order equations, there's like I said, there's very many more applications. Based primarily on the fact that solutions to second order ODEs, they can have what I call an oscillatory characteristic, and so it can basically kind of go and oscillate back and forth. And there are lots of physical phenomena that exhibit that behavior. Okay. So I would say kind of the most prominent application for second order ODEs is to measure vibrations of some kind. Okay. And in fact, for those of you here that are mechanical engineers, right, this class is a prerequisite to 431, which is our vibrations class. And so, this is kind of the main reason for that. Okay. And so vibrations has a lot of interesting applications. And so kind of the first one that kind of comes to mind is structural resonance testing. Okay. Okay. So we'll be going over resonance later on in the semester, but basically every physical object has a very specific frequency where if you force that object at that frequency, it's going to cause very large scale deformations, right? And so if there's a very famous video, it's shown in basically every structures of vibration class of the Tacoma Narrows Bridge. And so if you ever seen that video, it's pretty kind of crazy just how crazy those vibrations are. And that's partially due to resonance. Okay. For my civil engineers here, so resonance and vibrations is something that you have to be very aware of, because when you design buildings, especially in California where we get earthquakes are a thing here, you want to make sure that the building is earthquake resistant. And part of what that means is that, you design the building in such a way such that the resonant frequencies do not align with the earthquake frequencies. Otherwise, you have a building that might fall apart. Okay. Another interesting application for vibrations is in generating sound or music. Okay. And so what we perceive as sound is nothing more than just, vibrations or, oscillations of air pressure in the, traveling in the air, right? And so if you want to make music, usually you're going to create, a combination of different sounds at different frequencies. So, if you're designing like a musical instrument, you need to have a strong understanding of vibrations in order to do that. Okay. Okay. Another common application, again, you're gonna see me bring this up a lot just because it lends itself well, is circuits. Okay. Now we just did an example with circuits, and so we just did an RL circuit. But if you want to bring other components into the circuit, like a capacitor, you need to model those with second order ODEs. Okay. Right. So I can say circuits, but more complex. Right. Another example that we'll do kind of later on, and this will be one of your homework assignments too, is to design a shock absorber for a car. And so a shock absorber is nothing more than just a very heavily damped spring in your car, right? So when your car goes over a speed bump or hits like a pothole in the street, you want to make sure your car is not going to, vibrate like this. And so you need to design that system in order to, to damp out those vibrations. And a strong understanding of second order ODEs will help you do. Okay. So there's a lot of examples. I can kind of go on and on about the applications, but second order ODs is very good to learn just from these perspectives. Okay. Okay, so let's get into the mathematics behind it now. Okay. So for second order equations, we're going to make one assumption right off the bat. Otherwise, we're going to have a really hard time solving these. First assumption we're going to make is that we are going to assume that our equations are going to be linear. Okay. And so kind of recall what that means, from our discussion of integrating factors. So all of the dependent variables are only going to have a polynomial order of. Okay. All right. We're also going to make another assumption. Okay. We're going to make another assumption that all of the coefficients in front of the y terms are just going to be constants. Okay. It is possible to solve second order equations with non-constant coefficients, but it's a little bit beyond kind of what we want to do for this class. And so, just for the sake of simplicity, we're going to assume constant coefficients. Okay. Yeah.
Do you mean when you say in front of the y, is that the dependent or as in independent?
The independent variables.
The independent.
Yes. Yeah. So actually, let me write out the form, and then I think it'll see. Yeah. So the form that we're looking at is the following. So we have d squared y dx squared plus p times dy dx plus q times y is equal to R of X. Okay. So when I say the coefficients are constant, basically any coefficient that's in front of a Y term is going to be a constant. And so here we have P, that P there is multiplied by dy dx, and then we have Q multiplied by Y. These we're going to assume are constant. So these are not going to be functions of X. Yeah. Mm-hmm. All right. So it seems like a lot of assumptions, but you know, and it kind of is, but you know, you'll see that there are still a lot of really interesting systems that we can analyze here as well. Okay. All right. But before we get to that, we have a few more definitions just because we have you know, we have a new equation here. Okay. All right, first definition that we're going to have, and technically this definition applies to first order equations as well, but I think it kind of makes a bit more sense in second order to discuss it here, which is the idea of a homogeneous equation. Okay. And so we say a differential equation is homogeneous if it only has terms that involve the dependent variable. Okay. Another kind of simpler way to say that is that, you know, if your equation is in this form, a homogeneous equation has a right-hand side equal to 0. Right. So that R of X term, is interesting because this is the only term in our differential equation that does not involve Y in some way. And so if that term is 0, then we have a homogeneous equation. Okay. If that term's not 0, and so we do have something on that right-hand side, some function of X, then what we say is that we have an inhomogeneous equation. And and believe it or not, there's actually different techniques for solving this. Okay. Or I guess another way is you can, I think non-homogeneous is a bit more standard, but inhomogeneous, non-homogeneous, they're the same. Okay. Okay. Another definition that we'll have is this idea of linear independence. Okay. So linear independence does not necessarily have anything directly to do with the original ODE, but it is going to affect how we choose our solutions. Okay. Okay, so the idea with linear independence is that if you have two functions, okay, so we'll call them y1, y2, right? We say that they are linearly independent if they are the following. Okay. Okay. So given two functions, if this expression, and so if we take C1 multiplied by y1 of x plus C2 times y2 of x, okay? So we're essentially adding those two functions together and then multiplying each one by some constant, C1 and C2, okay? And if we set this whole thing equal to 0, okay, So y1 and y2 are linearly independent if the only way to make this equation true is if c1 and c2 are equal to 0. Okay. Right, so that's kind of the strict mathematical definition for linear independence. But I think of linear independence in kind of a simpler way. And so, if y1 and y2 have different functional forms, or in other words, they're different function types, then we can say that they're linearly independent. Okay, so let's do some examples that kind of illustrate this idea of linear independence. Okay, so first let's do an example of two functions that are linearly independent from each other. Okay, so let's say y1 is e to the x, and let's say that y2 is e to the minus 2x. Okay. So my argument here, or what I'm trying to argue, is that these two functions, e to the x, e to the minus 2x, are linearly independent from each other. Okay. So let's test that out. So if we make this linear combination here, so we say c1 multiplied by y1 plus c2 multiplied by y2, okay? We set it equal to 0. Let's go ahead and plug in our functions y1, y2. So we have c1 times e to the x plus c2 times e to the minus 2x. We set this entire thing equal to 0, okay? Now, if there's a way that we can specify values for C1, C2, where this equation is true for all values of x, then these functions would be linearly dependent on each other, okay? But since these are two different kinds of functions, so you basically have an exponent raised at two different values, there's no way to make this true unless C1 and C2 are equal to 0. All right. So essentially, two exponential functions with different exponents are linearly independent from each other. Okay. Okay. Now let's do an example where we have two functions that are not linearly independent. So they are linearly dependent on each other. Okay, so let's say y1 is equal to, let's say it's x cubed, okay? And then let's say that y2 is minus 3x cubed, okay? All right, so let's do the same thing. So let's make our linear combination. So let's add these two together, and then we'll multiply by c1, c2, okay? So you have c1, y1 plus c2, y2 equals 0. We plug in, we have c1 x cubed plus c2 times minus 3x cubed. Okay. Set that equal to 0. Okay. All right. Is there a way for us to basically set values for c1 and c2 to make this true other than 0? Right? There is, because, let's try making c1 equal to 3, okay? And then we'll make c2 equal to 1. just as an example. This is not the only combination that works. There's other ways to make this true, but we'll go with this one for now. Okay. And so if we plug those in, we get C1 is equal to 3. So we have 3x cubed, okay, minus 3x cubed, right? Because C2 is equal to 1. And we can say that this is equal to 0, okay? And so since there is a combination, or since there is a way for us to set C1, C2 to make this true, with besides 0, we say that this Y1 and this Y2 are not linearly independent. Okay. All right. But again, the way I kind of see this is that, y1 and y2 are both cubic functions. So they're both basically x cubed. And so they have to be linearly dependent on each other because, they're both the same kind of function, just that the constant in front is different. And so usually the constant in front doesn't make that big of an impact in terms of what kind of function it is. And so you have to see how the function depends on its independent variable. Okay. All right. Any questions on this? Okay, good. All right, so why is this relevant? So why are we talking about linear independence? Well, so second order equations have this really interesting property where you're actually going to get multiple solutions to the same second order ODE. Okay. In fact, we could even be a bit more specific than this. Second order ODEs will have exactly two solutions, at least to the homogeneous problem. Okay. And so one of the requirements that we have for these solutions is that they have to be linearly independent from each other, okay? I'm not going to run through the proof just because that kind of takes a lot of time and, it's a bit more on the mathy side. But, there's also important engineering reasons why we need to have our solutions being linearly independent. And, we'll cross that bridge when we get there, okay? Okay. And so for now, we're going to work under the assumption that we're looking for two solutions per problem. But what you're going to see later on is that once we start to get to non-homogeneous equations, we're actually going to add a third solution to it. And that third solution must also be linearly independent, okay? So no matter how many solutions you have to these equations, they all have to be linearly independent from each other. Okay. All right, so let's go ahead and start solving. Okay. All right, so how are we going to start to solve these equations? Well, kind of like what we did with integrating factor, there is a very clever and efficient way for solving these equations. the proof for it is not that convincing. So it's kind of a, hey, this works, let's use it kind of thing more than, let's actually derive something. Okay. So if you kind of remember from 250B, so this is probably something that was covered. So eventually we're going to work our way towards the characteristic polynomial. Let me kind of speak briefly about how we get it. Okay. Okay. So the most important kind of quantity that, or most important characteristic that we're working with here, especially relative to our first order equations, is the fact that all of our coefficients are going to be constant. Okay. So all of our P terms, they're going to be constants, right? Oh, another assumption we're going to make is that we're going to assume our equations are homogeneous as well. Okay. And so under those two assumptions, we are going to basically say that, under these kind of strict conditions here, our solution should follow a very kind of strict form, right? Because these are kind of both pretty restrictive. Now, what form should it take? Well, let's take inspiration from our first order equations. Okay. So let's apply these same assumptions to our first order equations, and let's see what that solution would look like. Okay. So if we apply the same assumptions to our first order equations, we basically assume that our coefficients are constant. So our P of X is just going to be P. And then we're going to assume the right-hand side is going to be 0. We have homogeneous, okay? So we end up with dy dx plus P times y is equal to 0, where in this case, P is constant. Okay. All right. So since we have a homogeneous equation, right? We actually have a situation here where we can separate the variables. Okay? So at this point, we don't really care what the value for P is. And so because it's a constant, it's just going to slip right out of any integrals that we do. Okay. Okay, so let's do this pretty quickly. So let's basically move that to the other side. So if dy dx is equal to minus Py. Okay. Let's divide both sides by y. Let's move the dx to the other side. So we have dy over y is equal to minus P dx. Okay. All right, and so we are now ready to integrate this. Right. I'm going to well, let's put the constant there. That's fine. So on the left-hand side, we get ln of y is equal to minus px plus c. Okay. We solve for y, we get y of x is equal to a e to the minus px. Okay. Right. All right, so what this quick exercise has kind of told us is that, if we apply these assumptions, and so if we have a homogeneous solution, if we have a homogeneous differential equation with constant coefficients, what we end up here is that we have a solution that is an exponential function. Okay. All right, and we did that for a first order equation because our methods for first order equations are a little bit more robust because they're first order. Okay. Now the argument here, this is kind of the hand wavy part, is that if we apply those same assumptions to our second order equation, we should get the same type of solution for our second order equations as well. Okay. Okay. Because we're applying the same conditions. And so the only thing that's different is that, we're going up in order, right? And so, by this logic means that, we should be looking for exponential solutions as well. It's a stretch, right? It's so, this is not something that I think normally, normal people would make that assumption just because, a lot of things do actually change when you go up in order. But let's try it out. Let's see what we get when we do make this kind of assumption. Okay. Okay. So if we're looking for an exponential solution, right, that means we can plug in something like the following. Okay. So we're going to make basically a generic exponential function, and then we're going to plug that back in. So we'll say y of x is equal to, we're going to ignore the arbitrary constants. We'll say this is equal to e to the lambda times x. Okay. Where lambda in this case is some constant. Okay, it's an undetermined constant that we'll solve for. Okay, so let's go ahead and plug that in. And so our second order equation, as a reminder, is d squared y dx squared plus p dy dx plus q times y. And since we're assuming our equation is linear, we're going to set the entire thing equal to 0. Okay. Okay. All right, so let's go ahead and plug this in. So basically everywhere we see y, we're going to plug it in. So we have d squared dx squared, second order derivative of e to the lambda x plus p times d dx of e to the lambda x plus q times y, so that's q times e to the lambda x equal to 0. Okay. All right, so next thing we have to do is we have to perform our derivatives here before we can simplify. Luckily, we're working with exponential functions, so the derivatives here are quite straightforward. So our second order derivative of this, of e to the lambda x squared, we get lambda squared e to the lambda x plus p times the first derivative of e to the lambda x, that's lambda e to the lambda x plus q, no derivatives to take on the last term, times e to the lambda x is equal to 0. Okay. All right. So now all the calculus is done. So we've taken our derivative. So all we're left here is an algebraic expression. Okay. First thing we'll notice is that every term here has e to the lambda x. So we can go ahead and factor that out and cancel it. because our right-hand side is equal to 0. Okay. So this, they're all common terms. So let's go ahead and get rid of all of them. Okay, we're going to divide both sides. And then what we're left with is lambda squared plus p times lambda plus q is equal to 0. Okay. All right, and so what we have left here is a quadratic equation, okay, which we can solve for our values for lambda. Okay. All right, and so you can solve these quadratic equations however you like. And so, I think some people are good with just doing it by eye, just looking at it and say this factor is this way. Kind of the safe way and kind of the it takes a little bit longer, but you're guaranteed to find the answer is use our quadratic equation. Okay. And so I'll give you the expressions for those here. So lambda 1. Remember, we're going to have multiple roots here. So we're going to have multiple solutions because this is a quadratic equation, right? So lambda 1 and lambda 2 is equal to, in this case, let's see, minus p plus or minus square root p squared minus 4 times q, all divided by 2. Okay. Where you get one value of lambda where that you apply a plus on the numerator, you get another value of lambda where you apply the minus. Okay. Okay. And so after you solve for the values for lambda 1, lambda 2, those will give you your two linearly independent solutions to the ODE. Okay. Right, so we have y1 here is going to be equal to e to the lambda 1 times x, and then y2 is equal to e to the lambda 2 times x. Okay. All right, so both of those should be valid solutions to your differential equation. You plug either of those in, and you're going to get your solution is going to be satisfied. Okay, but normally for these equations here, we don't display it, or we don't we don't report it as these two separate solutions. Usually we combine them together into one. Okay. Okay. All right, so what we say is y of x is equal to c1 times y1 plus c2 times y2. All right. So that's basically our solution procedure for second order equations. So for second order ODEs, we're going to form the characteristic polynomial, the characteristic equation for solve for lambda. Once we have our solutions for lambda, we're going to plug those in and form our two linearly independent solutions, and then take a linear combination of those to form our general solution. Okay, so this right here, this is our general solution to our second order ODE. Okay. All right. Any questions on how we got to this point here? Okay. All right. Cool. All right. So, that's our procedure. And, we're going to be spending a lot of time talking about these types of solutions here. Okay. So we only have about, maybe about 7-8 minutes left today. And so we'll talk about kind of some cases here, but depending on the values from lambda, it's going to dramatically kind of change the character and the behavior of solution. Okay. And so in particular, there are three different cases that we're going to go over. Okay. And they're all kind of cases that you can derive from the quadratic equation there. Okay. All right. So the first case, which is the simplest mathematically, is for cases when we have two real roots. Okay. So in other words, these are cases where lambda 1, lambda 2 are two distinct real numbers. Okay. All right. And so this will happen when basically the quantity under the radical or underneath the square root in the quadratic equation, right? So the square root of p squared minus 4q, okay? When this quantity here is greater than 0, then we have two real roots. Okay. The second situation that we'll come up with is when we have what's called a repeated root. And so in this situation, lambda 1 and lambda 2 are the same, right? It's just that, those it's a double root, okay? And so that presents an interesting challenge because, remember what we're working with is, both of our solutions, y1, y2, have to be linearly independent. But if both of the roots of the characteristic equation are the same, we're going to have to do a little bit of mathematical magic in order to get them to be linearly independent. Okay, so this happens when the quantity underneath that square root is exactly equal to 0. So happens when p squared minus 4q is exactly equal to 0. Okay. Okay. And then the last situation, this one's probably the most interesting. This is the one you'll kind of see, I would say, most often in engineering applications, just because, vibrations are kind of a big thing, is when you have what's called complex conjugate roots. Okay.
So that more in circuits, don't you?
You see in circuits, but then if you want to get any kind of oscillatory behavior like vibrations, you need to have complex conjugate roots. Because the solution for complex conjugate roots is sine and cosine. Yeah. All right, so these are situations when the quantity under the radical is less than 0. Okay. And that's significant because, if you have something underneath the radical that's less than 0, right? So in our quadratic equation, we have square root p squared minus 4q, okay? And so if that quantity there is less than 0, right? Taking the square root of a negative number gives you an imaginary number. right? And then, when you have an imaginary number, things get a little bit weird. But we are going to make use of basically Euler's formula, which basically converts a complex or imaginary exponential into sines and cosines, essentially. Okay, and that's how we got to cut that oscillatory behavior. Okay. All right, so those are our three cases, and so you can see that they're going to depend very strongly in terms of what's going to happen with our two roots. We're kind of an awkward spot right now, so are there any final questions? All right, so it's not really enough time to start solving problems, so we'll save that for next time. But so when we come back on Thursday, we'll go through these three situations here. We'll see what the solutions look like, and we'll talk about some of their applications, right? So thank you everyone for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday.
And so,
Yeah.
was that my computer that was not working, or was it the audio?
I'm not sure because I see the microphone coming up, but I have no way to actually verify.
I didn't sell online. Can I pull my laptop?
Oh, yeah. Because if this microphone's not working, then maybe this thing is faulty. But I didn't see any settings on here to say. But usually, if this microphone is going up and down, then it's sound should be coming. But I actually didn't even check the recording from last week. I kind of just posted it, so I think that might be a good test to see if it actually works. So.
You see the threshold, in the actual settings, it shows what the microphone is going to, and then threshold is a different distinct color.
I see.
That'll show whether or not it's within that range.
Yeah, let's check that. Sure. Let's see.
Yeah.
Well, this is the volume here. Can't even change this. Yeah, because I think the other
It's coming
microphone.
out. It's coming out.
What's coming out? Okay, good. Okay.
Sure, what was happening, but I will give it another try next week.
Sounds good. Otherwise, I was gonna return that angrily to Target. Spend money on that. So that should be working.
Yes, thank you so much for listening.
Thank you.
Anthony.
Oh, okay.
Yeah.